Welcome to this explainer. When we talk about hunting for extraterrestrial life, our minds almost always jump straight to lush, green, Earth-like planets, right? Well, actually, we're going to dive into a completely different kind of cosmic detective story today. We are heading straight into the dark, freezing, icy depths of our very own solar system. And trust me, the clues we're about to uncover are absolutely going to change how you look at the moons orbiting our giant planets.
So, think about it. Where is the absolute best place to find alien life? Like I said, we usually picture these warm, rocky worlds sitting at the perfect, comfortable distance from their sun. But scientists are increasingly pointing their fingers at frozen, totally desolate moons as the most likely places to harbor actual biology. And to understand how life could possibly survive so far away from the sun's warmth, we actually have to take a look right here in our own backyard first.
35 million years. To really get why icy moons are considered prime real estate for life, we have to look at extreme environments on Earth. Take Antarctica's Lake Vostok, for example. This is an immense, deep body of water that has been trapped underneath the East Antarctic ice sheet, completely isolated from the outside atmosphere for roughly 35 million years. It is literally cut off from the world.
And that brings us to the fascinating concept of subglacial lakes. These incredibly dark, isolated waters are basically naturally occurring ecological experiments. They absolutely prove that the fundamental basic reactions for life, they don't actually need the sun at all. Life can completely thrive in sub-zero temperatures, in the pitch black, relying entirely on the chemical energy and heat bubbling up from the Earth's interior.
Okay, so if we're taking this knowledge and hunting for life out in space, we need a sort of cosmic checklist. For any of these icy moons to actually be habitable, we're looking for three core ingredients. We need water, we need chemistry, specifically elements like carbon, nitrogen, and oxygen, and we need a reliable energy source. So let's see if we can hunt down these exact clues out in the deep solar system, starting right over at Jupiter's largest moon.
Now, how do you look inside a solid planet? There was this brilliant insight from researcher Joachim Saar, who thought, well, what about the aurorae? This led scientists to point the Hubble Space Telescope at Jupiter's moon, Ganymede. Because Ganymede is sitting right inside Jupiter's massive magnetic field, scientists noticed something super strange. The moon's aurora were actually rocking back and forth, being pushed by this hidden, invisible magnetic force from deep beneath the icy crust.
And that specific rocking motion, that was the ultimate smoking gun. It essentially proved that Ganymede is hiding a massive, deep, saltwater ocean completely underneath its ice. We are talking about an ocean holding more water than all of Earth's surface combined. It's just mind-blowing. So just like that, we've checked off our first crucial ingredient in a massive, massive way. But what about the chemistry and the energy? Let's take a trip over to Saturn.
When the Cassini spacecraft actually flew directly through these massive water plumes erupting out of Saturn's moon Enceladus, it scooped up some truly incredible data. The thermodynamic analysis revealed this perfect, sweet spot chemical environment, a highly specific zone that provides the exact right conditions for an energy-releasing biological process.
And that process is methanogenesis. See, Cassini literally tasted molecular hydrogen inside those geysers. That is huge because it points directly to deep-sea hydrothermal vents, where water is violently reacting with rock. It's driving the exact same chemical energy processes we see at the bottom of Earth's oceans. This state of chemical disequilibrium is exactly what ancient forms of life on Earth exploit to get their energy.
So at this point, we're building up this incredibly solid theory that all of these icy moons are just these vast, layered global oceans. But science rarely gives us easy answers. Recent gravity data from Saturn's largest moon, Titan, just threw a massive, unexpected wrench into everything we thought we knew. Let's look at what happens when the evidence points us in a totally different, but honestly equally fascinating direction.
Unlike Ganymede's confirmed sloshing liquid ocean, a recent reanalysis of the data showed something else entirely for Titan. Titan's strong tidal dissipation, which is basically the internal friction caused by gravity, actually prevents a global ocean from ever forming. Instead, Titan likely hides this thick, mushy, slushy layer of high-pressure ice beneath its surface.
But don't count it out, because this twist makes Titan even more fascinating. The lack of a massive global ocean doesn't mean the moon is dead. Instead, it has these localized, slushy pockets of liquid. And these pockets could be heavily enriched with the really complex organic molecules that are constantly raining down from Titan's thick atmosphere, creating these highly concentrated, incredibly unique little pockets of potential life.
To investigate these incredible organic niches, the upcoming Dragonfly mission is going to head straight for Titan. Dragonfly is literally a drone-like rotorcraft that will fly through Titan's alien atmosphere. It's carrying this amazingly advanced mass spectrometer, specifically designed to analyze the nitrogen chemistry and hunt for chiral signatures. Those are molecules with specific left-handed or right-handed shapes that act as undeniable fingerprints for biological life.
Meanwhile, zooming back over to Jupiter, we have another absolutely incredible mission taking shape. 45, that is the number of daring, intensely close flybys the upcoming Europa Clipper spacecraft is going to perform around Jupiter's icy moon, Europa. By doing these quick in-and-out flybys instead of staying in a steady orbit, the spacecraft can safely investigate the moon's ice shell and potential water plumes without getting completely fried by Jupiter's harsh radiation belts.
Now, the absolute ultimate objective of the Europa Clipper is to map Europa's surface in unprecedented high-definition detail. And why? Well, it's not just for orbital science. It's to map out the surface hazards and find the absolute safest, most compelling landing site. Because let me tell you, putting a physical lander down onto that alien ice is our next great leap.
Once that lander touches down, the real straight-out-of-sci-fi technology takes over. The plan is to unleash what's called a cryobot. This is a highly specialized probe designed to literally melt and drill its way straight down through miles and miles of thick freezing ice, just to reach that dark, hidden ocean below.
You can think of the cryobot as essentially a heavily armed downward drilling scientific submarine. As it makes its descent, it's going to analyze the ice composition and literally sniff the air in the tunnel for biological byproducts like methane. And to make sure we actually get all this precious data back to Earth, it's going to drop up to 44 radio transceivers into the ice behind it, creating a breadcrumb trail to maintain a connection through the shifting crust.
Then, once it finally breaks through the absolute bottom of that ice shell, the entire mission completely transforms. The drilling heat point drops away, and the Aquabot is unleashed. We're talking about an autonomous, AI-driven submarine dropped directly into a pitch-black alien sea specifically to hunt for life.
Surviving the absolutely crushing pressures of an alien ocean requires some serious next-level engineering. The Aquabot will utilize heavily reinforced spherical chambers to keep from imploding. And because it's operating deep, deep under miles of solid ice, mission control back on Earth literally cannot steer it. It has to rely entirely on its onboard AI, sonar, and thermal imaging to navigate the abyss completely independently.
Armed with lasers and extremely sensitive mass spectrometers, the Aquabot's entire loadout is built for one main thing: tasting the water. It's going to analyze water samples on the fly, hunting for those absolutely essential elements: carbon, oxygen, nitrogen, phosphorus, and sulfur, the exact building blocks that make up life as we know it.
Which really brings us back to why this all matters so much and what the big takeaway is here. Understanding the absolute temperature limits of life, which we currently think is between -13 and +121 degrees Celsius, tells us if these dark, high-pressure environments can actually support fundamental biochemical reactions. These icy moons push right to the very edge of those limits, and they're going to show us if life is stubborn enough to survive in the most extreme corners of our solar system.
There's a great quote from NASA's John Grunsfeld that really echoes the absolute awe rippling across the scientific community right now. He pointed out how a deep ocean under Ganymede's crust opens up exciting possibilities. It's a great reminder that our solar system's moons are absolutely no longer just dead, boring rocks orbiting in the dark. They're incredibly dynamic, geologically active, and potentially habitable frontiers sitting right on our cosmic doorstep. So the crucial takeaway for you today is that our exploratory focus has radically, fundamentally shifted. We've mapped the dusty, dry planets. We've done that. The next giant leap for planetary science isn't just taking a footstep onto a dry crater. It's a blind, daring dive into an alien abyss, miles beneath the ice. Exploring these subglacial worlds isn't just about finding some liquid water. It's about answering one of the most fundamental questions of our existence. Can the spark of life originate completely independently, entirely cut off from the energy of a sun deep in the pitch black? Because if it can, well, the universe is likely teeming with life in places we never even thought to look.
Which leaves us with one final incredibly thrilling thought for you to chew on. After decades of analyzing magnetic fields and blurry pixels from afar, a moment is actually coming. When we finally pierce that ice, and our submarine turns on its lights in those alien waters for the very first time, what might we find staring back at us from the deep?